In this video lecture, we're going to be going over how to write template classes in C++. And a good place to look for information on it is either Scott, section 8.4, or in my notes on generics in C, C++, and Java. And if you go to that page, you will find that there is actually just a list of advantages and disadvantages for C++, which we'll come to at the very end. But the main action occurs in a link called templates. So you've already should have used templates in 140 and 302. And here's some examples. Here's a doubly linked list of integers. Here is a doubly linked list of pointers to payroll records. And here's a hash table whose keys are ints and whose values are strings. You might notice that one difference between C++ and Java in terms of the generic classes is that C++ allows primitive types to be instantiated as type arguments as well as objects. Also, like in Java, once you've declared and instantiated the variable, you now just treat it like an ordinary variable and don't have to put any of the brackets or the like. So for example, in the above declaration, we declared A as a D-list. Now we simply call insert before cursor and pass it the value 3. The same is true for our other variables that we declared. Now, C++ also provides function templates, just like Java provides generic methods. We're not going to talk about them much in this class except in the context of method bodies for class templates. Now, what you do not have experience doing is writing class templates. And unfortunately, the syntax is much more complicated than it is in Java. So when you're going to create a template class, you always start with this kind of line, the keyword template, and then in less than greater than braces, your set of type parameters. And if it's going to be a class, you need to prefix it with class. If you're going to use a constant, which you can do, and which will be illustrated in a moment, then you would actually declare it with the appropriate constant type. So once you have the type parameters in place, you then can go ahead and declare your class. So we have here an example of a dynamic array that gets resized if the amount of memory it currently has allocated gets exceeded. So you can see that we have the template header, and that in fact we have declared an integer constant array size, which is equal to 12. So in this sense, it's a little bit like how interfaces in Java can have constants declared for them. And this is considered the int array size equal 12 is considered a default type parameter. It could be omitted in the actual class declaration, as we'll see later. So once we have that template, we now go ahead and define our class as we ordinarily would have, with the one big difference that we often replace a specific type with a type parameter. So here we are storing elements, values of type elements. So get value returns the element at a certain index. Set value stores a value of type element at some index. And you can see that array size is used to provide a default initial size for the array. Finally, down in the instance variables, you can see that we're using a heap allocated array for our data, and it's a pointer to our element type. Now when the C++ compiler instantiates one of these, let's say that we had something that looked like the following. So we're declaring a dynamic array of integers and giving it an initial size of 15. So when C++ actually instantiates this code, it's going to treat it like a macro. It's going to replace all instances of array size with the value 15. So right here, this is going to become size equals 15. And then all instances of element are going to get replaced by int. So this would become int get value. This would become int value. And down here, this would become int star data. And now the C++ compiler would compile a copy of this code. The C++ compiler creates separate copies of template code for each set of type arguments that are given to it. So for example, if I have another array, let's say array of payroll records, and this time I'm leaving off the default parameter, it would create a separate piece of code, instantiate it with payroll star, and compile it. So once you've declared this declaration would go into a .h file, and now you have to write the methods for a template class. And there's two ways to do it. It's actually acceptable to put your methods for a template class in the .h file. In fact, it really streamlines the declaration. So here, I've done that and put the method bodies in the .h file. So for example, my constructor is simply creating or assigning the initial size to size, and then is creating a new array of elements with size sc and assigning it to data. Or down here, you can see for the get value, it returns an element and checks to see if the index is less than 0, or if it's greater than or equal to the size. In either case, we have an index out of bounds situation and it prints an error message. And otherwise, it returns the data element at location index. And I'll let you peruse the rest of the code at your leisure. Now, one dangerous thing about putting your method bodies in a .h file is that it is a very strong directive to the C++ compiler to inline these method bodies. You can see that get value right here and set value right here have pretty significant method bodies. So if you use these method calls in a lot of different places in your code, this could considerably increase the eventual size of your executable. So you should think long and hard before you succumb to the convenience of putting method bodies into your .h files. So you can also, just as with normal class files, put your methods into a separate .cpp file. If you do that, then you're going to have something that is going to look like this down here. So let's start out first with our class declaration. Let's say we have a function y. It returns type 1, taking type 2 as an argument. So in the .cpp file, you need to repeat the entire template header. So up here you see the template header for the class. It gets duplicated for each of the method bodies. Then the return type, as you're used to, and then the name of the class, as you're used to doing, except that you now have to include all of the type parameters with that class name. Then the usual colon, the name of the function, and then your type arguments. And it's not necessary that these all be type arguments. You might have actually had something that was simply another argument, like say int arg2. So it's not required that they all be type parameters. So here's a sample definition of the method bodies for dynamic array. So here is the constructor again, and you can see I've repeated the full template for the class, although one important thing is you'll notice that I did not say array size equals 12 anymore. Back in the original declaration, I did say array size equal 12. The C++ compiler is very finicky about this. If I put array size equal 12 here, it will give me an error message. So now I simply set my size equal to SC, and again my data to be new element. The other thing I want you to notice is I'm also not setting size equal to array size here. I did that also up in the .h file, but I do not do that in the .cpp file. If I do, C++ gives me an error message because it thinks that there is potentially a clash in the default sizes. Okay, and here's a little bit more complicated looking beast for get value, but again we've just repeated the template header, then the name of the class with its type parameters, colon colon, and then the name of the function. Again, I'll let you look at this function on your own. You should be able to figure out what it is doing. And you've already seen me give a couple sample declarations for the dynamic array. So the first one provides both type arguments, thus overriding the default value of 12 I gave for array size. The second one only provides the type parameter int, and it omits the value for array size, hence the default value of 12 gets used. And finally, here's a sample driver for my program. So in this case, I'm declaring data to be an integer array with an initial size of 15. I actually store 1,000 values in it, each of them by adding 2 to I and storing that value. Then afterwards, I iterate through it and print every 50th value. And finally, at the end, I print the size. And you'll notice that one very important item here is my include of dinarray.cpp. You would never do this if it was a regular class. You would use a separate compilation of dinarray.cpp. However, template classes cannot be compiled because they are essentially like macros. They're not executable code until you've instantiated them. So you have to include the .cpp file in every file where you want to use that template code. And you'll notice that in dinarray.cpp I included dinarray.h, so that gets the dinarray.h in. Now if I had put everything into the .h file, then instead of saying include dinarray, I would have said include dinarray.h. The final thing I want to do is just show you that this works. So here's my dynamic array driver.cpu, just as I showed you. I can compile it as I ordinarily would and run it. And you see that it prints out every 50th value and size at the end. Now, I just want to do a couple things to show you how awful it is to try to debug the compiler messages. So let's say that I actually forgot here to not put array size. So I put size equal array size there, as well as in the .h file, like that. Okay, so here it is again in the .h file. So I go to compile and I get redefinition of default argument. Okay, that's actually pretty good. That's not too bad. Let's go and do another example. Let's mess up and forget to put the template there. So we're just going to use dinArray, and we're going to forget to use its template parameters. Okay, and now we're saying dinArray expected a class or namespace, and there's really no indication that the problem was you left the type parameters off. So debugging code that involves templates can be very difficult, and you just have to be very careful about details. So let's wrap up by just looking at the advantages and disadvantages of C++ templates. The advantages, okay, they provide us a good way to specify generic data structures and generic functions. Their disadvantages are numerous. The code is very complicated to write, to debug, and to understand. Secondly, the compiler has to create a copy of the code for each different set of type parameters. Finally, because the templates cannot be compiled until they've been completely expanded with the type arguments, the error messages are almost unreadable. And finally, remember that with Java, if you wanted to ensure that a class or generic method was getting objects that supported certain operations, you simply made sure that you put a so-called upper bound on the type parameter. You specified a super type, and then any type argument had to be some subtype of that super type. C++ does not have that way of specifying in a template that a certain operation, such as a less than or greater than comparison, must be supported. So someone who is simply looking at your template code might not realize that it relies on a certain operator or a certain method to be declared, would go ahead and try to instantiate a variable with some type arguments, and then only at compilation get some kind of error message saying that this method or operator is not supported. So we would say that that C++ supports an implicit requirement for certain operations, whereas Java supports an explicit set of requirements or specifications. That concludes this videotape on C++ templates.